Swayam Prabha. Digital India. Educated India.
So this is called a step response because the input is assumed to step. Okay. So let's say you have a first order circuit. That means that you have one effective capacitor and you take any branch quantity there. So let's say Vx or the current Ix. Okay. And the only condition is that it be a first order circuit. Okay. So for instance, I could go on with this, right? I could do this. This is also a first order circuit with some caveats that when you set the source to 0, I will get this capacitor in parallel with a series combination. Like I said, the series combination always comes with some subtleties, but we'll ignore those things for now and call that a first order circuit. Okay. Now, a step response means that the input, or it could have multiple inputs, but let's consider a single input which steps up. Okay. The response of any voltage or any current in the circuit, it could be capacitor voltage, it could be anything else, okay, will be of this form. I'll write it for voltages final plus Vx initial, which should be taken as 0 plus, okay, because there could be something happening between 0 minus and 0 plus. It could be a jump, okay. Vx final. Final of course means infinity. So I could also write this as Vx of 0 plus minus Vx of infinity. And this part, this is the part that dies out. That's the natural response, right? And this will be multiplied by, let me move this a little bit. Exponential minus t by tau. Okay. Now, to be able to write this, you can first of all write down the differential equation and formally try to solve it. Okay. Then you may have to introduce this Dirac deltas or Dirac impulse functions and try to balance the left and right side and solve it that way. Okay. But now that we have solved it for a few cases, we can write down some general rules. So to write this response, you need all these quantities, Vx of infinity, Vx of 0 plus and tau. Okay. Now it's assumed that some initial condition is given, usually the initial condition on the capacitor. Okay, that means that usually the voltage on the capacitor just before the step is applied, that's what is given. Okay. Now from that you have to calculate what Vx is. This element may not be the capacitor, it could be anything else, right? For instance, in my RC circuit, I could be trying to write down the equation for the current through the resistor or the voltage across the resistor. Okay, so it could be any branch quantity. Okay. So from the initial condition given and the value of the input at t equal to 0 minus, you can find all the branch voltages just by using circuit analysis, right? So just by using KVL and KCL, you will be able to get this. Okay, in a first order circuit, you only need one initial condition. So the input source is also known. I mean, it's known for all time. So obviously, you know it for 0 minus also. Okay. So what I mean by this is, let me take an example, a simple example. So let's say this is steps from 0 to 5 volts. And the initial condition on this is minus 2 volts. Okay. This is given. Okay, and what I am interested in is the current IR. So I want to write an equation for IR of t. Okay, so first of all, what is IR just before the step is applied? Let me say this is 1 kilo ohm. So what is it? So it is plus 2 volts. So this is plus 2 milliamps. Okay, so initially at t equal to 0 minus, I have 0 volts here with respect to this ground and minus 2 volts there. Okay, so it is plus minus 2 volts in that direction. So the way I have marked IR, it is plus 2 milliamps. So now this, what is it immediately after you apply the step? So in this case, so when you go from 0 minus to 0 plus, first of all, you have to see if there are any loops of voltage source and capacitors alone. Okay. In other words, the way to do it is by you ignore all the resistors. You have only voltage sources and capacitors. Okay. Or sources and capacitors. With that, you can solve for any jump in capacitor voltages. Right. In this case, what is the value of the capacitor voltage just after applying the step? It will be minus 2 because there are no loops of voltage sources and capacitors. Or if I remove the resistor, the whole thing is an open circuit, nothing changes. Okay. So from that you can calculate IR of 0 plus. What is that? This is 7 milliamps. Okay. And the final value of IR, what is that? How do you find that? You have to open circuit the capacitors. Okay. Because we are talking about piecewise constant voltages. So the steady state also will be a constant voltage across the capacitor. So that means that the current through the capacitor will be 0. Okay. In this case, it so happens that IR is the same as the current through the capacitor. So this is also 0. Okay. So now what is the expression for, and by the way, what is the time constant? Let's say this is 1 nanofarad. In this case, it's very easy. What is that? 1 microsecond. Okay. So what is the equation for IR of t for t greater than 0? 7 milliamps exponential minus t by 1 microsecond. Okay. That's all. I don't know if you are in the habit of doing this, but sketching possible solutions gives you a lot of insight. Okay. It's not very precise because you are doing hand sketches, but it can give you a lot of insight. So what happens is IR, which is plus 2 milliamps, just before t equal to 0, will jump to 7 and then decay to 0. Okay, so that's what it will look like. So you can do this for any arbitrary circuit. The only complication will come, additional complication is when you have loops of voltage sources and capacitors. So the way to go about solving for these things is first you determine the time constant. This is this, you set sources equal to 0 and the effective capacitance times the Thevenin resistance across it, that is the time constant. Okay. And then you determine values at t equals 0 minus. This is from initial conditions, okay, and some regular circuit analysis. And that is from t equal to 0 minus to 0 plus, it can jump. Now, of course, you know that it will happen only if you have voltage source, capacitor loops. Now, even otherwise, if you are not able to identify, you simply open circuit all resistors. The basis for doing this is the following, right? If you have any discontinuities at all, the currents through capacitors will be infinite, and the currents through resistors will still be finite as long as all the voltages in the circuit are finite. So you have these nodes where you have finite currents from resistors and possibly infinite currents from capacitors. So you remove all the finite currents and it will not change anything. Okay, clearly any finite value is negligible compared to infinity. That's the idea here. Okay, so you open circuit all resistors and do the circuit analysis. When you have voltage source capacitor loops, you have to do it based on charge, which is the same as saying you do it based on this Dirac delta functions of current. Okay. So you open circuit all resistors and determine capacitor voltages. But anyway, by inspection of the circuit, you should be able to tell whether there are loops containing voltage sources and capacitors or not. Okay. So this will tell you the value set. From this really. Okay. They also determine this is by this again, you open circuit all capacitors because we are applying piecewise constant inputs. We expect voltages across capacitors also to be piecewise constant. So when the voltage across the capacitor is constant, the current through that is 0. That's why we are open circuiting it. This is not valid for any other type of input. Okay, if you had input that was going up and down, you expect the capacitor voltage also to be constantly changing. In that case, clearly you can't open circuit anything. There will be currents through that. So only because of this piecewise constant nature of the input that you can do this. So finally, the solution would be of this form. I've written it in terms of voltages, but it could be currents also. This is 0 plus. Okay. So it's to find out this that you have to find out if there are any discontinuities at t equal to 0. Okay. So you should be able to analyze these things without actually going into details of the differential equation. Okay. Whatever I write as 0 here is the instant of the step. And by the way, the step, you can have multiple steps. You treat it as first you apply some step, it will reach some value, not necessarily the final value. You determine what that is, use that as the initial condition for the next step. That's all. Okay.